All right, so in this video we're going to be talking about Lewis acids and Lewis bases. So acid-base reactions can also occur without proton transfer. So in the last video we discussed Bronsted acids and bases, right? Proton donors and proton acceptors. But this time we're going to be talking about Lewis acids and bases, and Lewis acids are an electron pair acceptor, also called an electrophile. And a Lewis base is an electron pair donor, also called a nucleophile. Right? And what these terms mean, electrophile, is it's an electron-poor species, right? So it wants to accept electrons. And a Lewis base, this nucleophile, it's an electron-rich species, so it wants to give away electrons. And we'll be talking about these in more detail in a later chapter. But looking at this example up here, right, we can see this reaction has occurred, right? And this might be kind of obvious just based on like what this final structure here looks like, but let's take a look at what each of these compounds are in terms of their Lewis acidity and Lewis basicity. Right, so looking at this first example here, right, this boron-containing compound, right, it has those 3 fluoride bonds, that's it. And remembering from what we know about boron, right, is it's a trivalent species, right, and it does not have a complete octet, right? It has a empty p orbital that it wants to get filled so it can complete its octet. And currently it does not, so it wants to accept those electrons, right? So this is our Lewis acid. And of course the oxygen, right, it's not drawn here, but there are 2 lone pairs on it, right? And that might be an obvious indicator already. This will be our Lewis base, right? It'll want to accept, or it'll want to donate those pairs of electrons, right, to the Lewis acid. Right, so if we're going to draw arrows, like with the Bronsted base and acid reactions, we would do it like this. We would choose any one of these lone pairs and just draw the arrow like this, where we're showing that there is a pair of electrons that has gone from this oxygen here to the boron. And now we can see over here, right, the boron has its octet complete, right, it's happy, and the oxygen still has a octet here. We'll draw on the lone pair just so you can see. Right, so the oxygen is happy with that octet. And if we were to sort of show it like really clearly where this new bond came from, we could draw it with this, we could draw it like this, right? So that new bond came from this pair of electrons right here that donated into the boron, right, making that new bond. Right, so I hope that's clear. Right, and so we can use Lewis acid and Lewis base interchangeably with Bronsted acid and base, right? We couldn't call this a Bronsted, well, we couldn't call this a Bronsted acid, right? Because it's not donating, or it's not donating a proton, right? And a Lewis base, right? It's not accepting a proton. But we could call Bronsted acid and bases Lewis acid and bases, right? So for majority of the rest of this chapter and probably semester, whenever I call something an acid or a base, I'm primarily referring to it as a Lewis acid or Lewis base, right? Because these terms are more general in terms of what they mean. So looking at these following examples, indicate whether they are Lewis acids, Lewis bases, or if they could be both, right? So going through the examples here, looking at our first one, right, we have a carbon with a missing hydrogen. So it has a positive charge, no lone pairs on it, not a complete octet. There's no way it could be a Lewis base, right, because it can't donate a pair of electrons. It has no electrons to donate. So this would be a Lewis acid, right, because it wants to accept a pair of electrons, right? It is an electrophile. Again, our next example here, we have water. Let's draw the lone pairs on here for clarity. We know that water, right, with those lone pairs, can act as a Lewis base, right? It can donate those electrons. But we also know, because of the polarity of that oxygen-hydrogen bond, that it can also accept electrons. right? It can act as a Lewis acid. And we already know this from our previous video that water can be an acid or a base. So what about this example here, right? We have our nitrogen, 3 hydrogens, and a carbon group attached to it, right? Nitrogen has a lone pair. So we know already that it can be a Lewis base, right? Because it can give away those pair of electrons, right? It can be a nucleophile. But we also know, again from a previous example, that the hydrogen can get taken away, right? It can get attacked and then have that pair of electrons between the hydrogen and nitrogen put onto the nitrogen to give it a negative charge. And it is still pretty circumstantial, right? If you have a strong enough Lewis base in a reaction, it'll take away that hydrogen, right? Conversely, if you have a strong enough Lewis base, I got confused. If you have a strong enough Lewis base, it'll take away that hydrogen. If you have a strong enough Lewis acid, the lone pair will attack, right, the relevant acid source to make this your conjugate acid, okay? So this last example here, very similar to boron, right? Aluminum is right underneath it on the periodic table, so it's also trivalent. So it wants to accept a pair of electrons to complete its octet and have the noble gas configuration, right? So it's also a Lewis acid, right? I hope that makes sense. And it couldn't be, right? This couldn't ever be a Lewis base because it doesn't really have any electrons to donate to, right? For the most part, if something is both a Lewis acid and Lewis base, it'll look kind of similar to examples here with water and this nitrogen-containing compound where they have an electronegative atom attached to a hydrogen, and that electronegative atom has a lone pair on it. So when we're talking about Lewis acid-base reactions, and Bronsted acid-base reactions, right, I showed curved arrows to show the flow of electrons. But I wanted to kind of hone in on like what exactly is going on when I do that, right? So being sort of general here, right, we'll have B for base, not boron. Right, we have our Lewis base. We could also call it a nucleophile. Right, and we just have a proton, right, positively charged hydrogen. And this, of course, is our Lewis acid, right? It wants to accept a pair of electrons. So when we do this, right, when we draw our curved arrows, we're always going from the source of electrons to the thing that wants to accept them, right? We're always drawing that flow from the electrons and to the thing that the electrons are attacking. So when we do that, the lone pair is no longer there, quote unquote, because it's no longer a unshared pair of electrons, but it is a shared pair of electrons between the former Lewis base and former Lewis acid, right? We're having that new bond be formed between them, right? And so when you're doing these reactions, you're drawing the curved arrows, you don't ever want to show the curved arrow going towards the source of electrons, right? You wouldn't ever want to draw it this way, right? Because that's not correct, because you're drawing it from the positive source to the negative source. You always want to draw it going from the negative and towards the positive, because you're following where the bonds are forming or potentially breaking, right? So drawing it the way I have down here is just not correct. I'll give you another quick example of that in more acid-base terms, right? Let's say we have our ammonium here, right? And then we have an acid. Right? So we have a Lewis acid and Lewis base. So if we were to draw the flow of electrons, right, we do it like before, we're showing the electrons going from the nitrogen and towards that hydrogen, right? And when we do that, now we run into an issue. Because if we were to just draw the bond as is, we would just have a bond going from the nitrogen to the hydrogen, which wouldn't make sense, right? Because that would give hydrogen way too many electrons around it. So we have to show that bond breaking, right? So this breaks onto the oxygen, right? And it kind of reiterates a point that this whole thing, right, it's a Lewis acid, right, because it is accepting electrons, right? In this whole case, right, this oxygen is accepting the electrons from the hydrogen-oxygen bond onto it, and the nitrogen over here is donating electrons, right? It's giving them away. So when the reaction is finished, we now have ammonium ion. So this is now our conjugate acid. And then we have our conjugate base, which is a newly formed anion with that negative charge on the oxygen. Right. So I hope that makes sense, and we'll get a lot of practice doing these curved arrow mechanisms. But this is pretty important to know, and it's important to keep in mind that the flow of electrons is always from the source to where they're going. Even that bond between the hydrogen and the oxygen, right? That shared pair of electrons, we're showing it moving from in between the hydrogen and oxygen and onto the oxygen itself exclusively, right? And just for clarity, I can even kind of draw this lone pair in red, right? So it's kind of clear where that came from. So we'll do this example in class, but on your own, before lecture, try this. Try to label the following reaction with the appropriate terms: acid, base, conjugate acid, conjugate base, and try drawing out the mechanism using that curved arrow format.